All right, let's get started with 1-4, complex numbers, quadratic equations in the complex number system. So we're going to introduce imaginary numbers in this section. So up till now, we have not been able to square root negative numbers, right? Hasn't been allowed. So we're going to introduce complex numbers where we can square root a negative. So real numbers, we cannot square root negative 1. Complex, if we say now we're talking about complex numbers, the square root of negative 1, we're going to call that thing I. So I is defined as the square root of negative 1. Therefore, if we squared both sides, I squared just becomes negative 1. All right, so that's the new thing that we're going to be dealing with in this section. So, and there's, we erase this so we can see this. If we have a real part and a non-real part, A is your real number, and then B is your non-real number because it's going to have an I with it. So like 5 plus 6I, 5 real numbers plus 6 imaginary numbers. All right, and that makes up a complex number, a real part and an imaginary part. All right, let's do some things with these complex numbers. Let's add, subtract, multiply, and divide them. So, first up, A plus BI equals C plus DI if A is the same as C and B is the same as D. This is the equality of complex numbers. All right, so 5 plus 6I is the same as 5 plus 6I. Here's the thing we're going to be using more than, or a lot. A plus BI plus C plus DI, what we do is we add up the real numbers, we add up the imaginary numbers. So we'll see that in an example in a second. And if we subtract the real numbers, A minus C. We subtract the imaginary numbers. All right, so let's try one of these on for size. In A, we're going to say 3 plus 5 and get 8. We're going to say negative 2i plus negative 4i and get negative 6i. And so our answer is 8 minus 6i. So in B, what's 3 minus 5? Negative 2. What's negative 2 minus negative 4? Positive 2i. So that'd be your answer on B. Combine your real numbers with your real numbers, imaginary with imaginary. Pause the video, try problem 13. Okay, what happens if we multiply? Let's try this and then we'll see the formula. FOIL this out. 3 times 5 is 15. Outside is negative 12i. Inside is minus 10i. Last is plus 4 times 2 is 8i squared. Now, 15 minus 22i, we're going to combine those like terms. But remember that I squared is negative 1. So it's going to be 15 minus 8 to get 7. This 15 plus negative 8 minus 22i. All right, so I squared is going to turn into negative 1. And so if we look at that, we've got ourselves a formula here. The formula, if we're multiplying, is going to be AC. So 3 times 5, 15, minus BD, minus negative 2 times negative 4, so minus 8. That'll give you 7. All right, and then we can go AD plus BC. That would give us 22. You can memorize this formula if you want to. I think it's probably easier to just do the foiling like always. And remember that I squared turns into negative 1. All right, so whichever way you want to do it, try problem 19. Okay, conjugates. We've talked about conjugates before with radicals, with square roots. A complex number also has a conjugate, and it's the same thing we've been doing before. A plus BI, the conjugate. Remember, the conjugate is the bar over the top of it. The conjugate of A plus BI is A minus BI. Don't switch A. A stays just as A, but the sign in between changes. All right, so find the product of the complex number 3 minus 2i and its conjugate. So 3 minus 2i times 3 plus 2i. Let's go ahead and FOIL this, but we shouldn't need to because this is 9 minus 4i squared. Right? We should be able to do this right away. This is the difference of squares. And this is going to be 9 minus 4. Remember, I squared is negative 1. So this is 9 plus 4, otherwise known as 13. So your answer here is going to be 13. We got ourselves a formula. If you multiply the conjugates, it's a squared plus b squared. 3 squared plus 4 squared. 9 plus 4 is 13. All right, so let's see if we can get this into standard form. So we're going to need to multiply 1 over 3 minus 2i. Can't have imaginaries in the denominator, so just like we can't have radicals, multiply top and bottom by the conjugate. This should look familiar. This is the same way we rationalize denominators. You can do the same thing with your imaginary numbers. So the numerator is 3 plus 2i. The denominator is 9 plus 4. So 3 plus 2i over 13. And that would be your answer. Okay, let's try one more. Let's do this one in standard form. 3 minus 2i over 5 minus 4i. We're going to multiply by the conjugate. 5 plus 4i, conjugate of the denominator. 5 plus 4i. So let's FOIL the numerator. We got 15. We're going to have, what do we have here? Plus 12i minus 10i, and then minus 8i squared. That'll turn into a plus 8. So 23 plus 2i all over 25 plus 16, which is 41. So 23 plus 2i all over 41. All right, 27. Try that one. Okay, so let's see some examples here. What's z over w if we're given two different expressions? This would be 3 minus I over 2 minus 5i. Again, conjugate, 2 plus 5i over 2 plus 5i. We're going to end up with 6 plus 15i minus 2i minus 5i squared in the numerator, all over 4 plus 25. So we're going to end up with 11, because the 6 plus 5 plus 13i all over 29. What's the conjugate of z plus w? All right, let's just do z plus w first. So z plus w is going to be 5 minus 6i. What's the conjugate of that? 5 plus 6i. And then what's z plus its conjugate? So 3 minus I plus, the conjugate would be 3 plus I. We're going to get 6. The i's would cancel out. All right, and that's really the whole reason we're doing the conjugates, is to make the i's go away. See if we can get rid of them. Okay, so the conjugate of a real number is the real number itself. So the conjugate of the conjugate is, we start back over. That's like saying square a square root. All right, if we do the conjugate of the whole thing, we could split it up and say the conjugate of one plus the conjugate of the other. This works. And if we want to do the conjugate of a product, we could find the conjugate of each one and then multiply them together. That would work as well. All right, last thing we got to look at here in this section is what happens with all our i's. I to the first is just I, square root of negative 1. I squared is negative 1. And now what's I cubed? Well, I cubed is going to be I squared, which is negative 1, times I. So negative I. I to the fourth is I squared times I squared, negative 1 times negative 1, so 1. And after that, I to the fifth, we can break that up into I to the fourth times I, and I to the fourth is 1. So we just start back over. So every fourth, we're just going to repeat. I to the eighth is the same as I to the fourth. I to the seventh is the same as I to the third. I to the ninth would be the same as I to the fifth, which would be the same as I to the first. So knowing that, what are these two things? Well, I can split this up into a multiple of 4, which I know is 1, and whatever's left over. So 1 times I, or just I. 83, 80 is a multiple of 4. What's left over? 3. So this is going to be I cubed. And I cubed is the same thing as I squared times I. I squared is negative 1 times I, so just negative I. All right, let's take a look at this. Let's FOIL all the way out the triple. We have a pattern for this. A minus b cubed is a cubed. Let's see, there's a minus in there. Minus 3a squared b plus 3ab squared minus b cubed. Let's plug it all in. A cubed is 27 minus 3 times 9 times bi. So what do we got here? 2i plus 3. A is 3. B squared is going to be 4i squared. And then minus 8i cubed. Okay, so we'll have to do that I cubed at the end. 27 minus 27 times 2 is 54i. 3 times 3 is 9. Times 4 is 36. I squared is a negative, so minus 36. And then this is going to turn into negative 8i squared. And I, remember this is just the same as negative 8. So this is going to turn into positive 8i. Instead of negative 8i cubed, positive 8i. So let's put this all together. I see negative 9 minus 46i. Okay, so it's all going to come together. All right, 33 and 41 are yours to try. Okay, now what happens if we do quadratics using complex numbers? Same thing that we've always done, except for now we can square root negatives. So now, if we do the square root of negative 1, we don't say no solution, we say I. Instead of this, we're going to have 6i. 32 splits up into 4 times 8, oh, sorry, go bigger than that, 16 and 2. So we're going to make this 4i root 2. Okay, because we take the I out to make the negative go on the outside. Let's take a look at an equation. X squared plus 25 equals 0. Let's get the x squared by itself, negative 25. Let's square root. X equals the square root of negative 25. What's our answer? X equals plus or minus 5i. Okay, instead of plus or minus 5, plus or minus 5i. All right, solve each equation in the complex number system. X equals negative 16. I wonder if something didn't copy down there. This is probably x squared equals negative 16. Let's make the problem like that so we can solve it. Square root both sides. X is going to be plus or minus 4i, not just 4. 53, give it a shot. All right, so again, here's your quadratic. If we solve this using the quadratic equation, let's see what we would get. Negative b, it would be positive 6 plus or minus the square root of 36 minus 4ac, so 4 times 13 is 52, all over 2a. So we've got 6 plus or minus the square root of, we've got a negative 16 all over 2. We used to say no solution, no real solutions, but now we have a complex solution. 6 plus or minus 4i over 2, which gives us 3 plus or minus 2i. Go ahead and try 59. Okay, so this was the discriminant, and before, if the discriminant was negative, we would have said no real solutions. Now we say there's actually 2 solutions, they're just complex. There's still no real solutions, but they're just complex solutions. And these solutions are going to be conjugates of each other. So if we go back here, 3 plus 2i, 3 minus 2i. Those are conjugates of each other. So if you have a negative square root, you have to get 2 answers, but they're going to be conjugates. All right, so let's take a quick peek at these and determine what kind of solutions we could get. So this is going to be, remember the discriminant, b squared minus 4ac. So 9 minus 4 times 2 times 1, 9 minus 8. We're going to have 2 real solutions. It's bigger than 1. Sorry, it's 1. It's bigger than 0. B squared is 4 minus 4ac. This is way bigger than this. We're going to be less than 0 here. So we're going to have 2 imaginary solutions. Notice that I didn't even go far enough to even figure out what this part is. Don't even care. I know it's bigger than this. We're going to be smaller than 0. B squared is 16 minus 4ac. 16 minus 16 is 0. We have 1 real solution that has multiplicity of 2. It repeats twice. All right, 73 is all yours. Okay, that's it. Any other questions? Make sure we go over them in class. Good luck with those problems.